You ever feel like technology is just moving way too fast to keep up? I mean, every year there's a new processor, new memory, new everything. Well, what if I told you that the big, fundamental ideas powering that shiny new machine on your desk are actually over 60 years old? Let's peel back the layers and see what's really going on under the hood.
Okay, so take a look at this. You've seen an ad like this a million times, right? It's just this dizzying list of acronyms and specs. Core 2 Duo, DDR2 SD RAM, SATA hard drive. It all sounds so incredibly advanced, like something that could only exist right now. It feels like the language of progress, doesn't it? But what if it's all just dressing on a foundation that hasn't really changed at all? And that brings us to this incredible quote from Dr. Irv Englander. He says that the core concepts, the ideas that really matter in computer architecture, have barely changed in 6 decades. So how is that even possible? How can that crazy complex machine we just saw be based on principles that are 60 years old? Well, that's the mystery we're going to solve. To solve it, we have to look past what I call the illusion of new. We need to peel back all those modern layers and get to the core, timeless concepts that make it all work. And we're going to start with the absolute biggest idea of them all. This is the blueprint for every modern computer, the stored program concept. Before this idea came along, if you wanted to change what a computer did, you had to physically get in there and rewire it. It's wild. But the stored program concept was a total game changer because it said, hey, what if the instructions, the computer's to-do list, are just another form of data? Think about that for a second. It meant a computer wasn't fixed. It could be a calculator one minute and a word processor the next, just by loading a different program. This single idea is what gives us the incredibly flexible machines we have today. Here's a great way to picture it. Think of computer memory like a giant wall of mailboxes. Every single box has its own unique number on the front. That's its address. But inside, who knows? You could have a to-do list, which is like an instruction, or you could have a photo, which is data. The computer just knows it needs to go to mailbox number 1776, open it up, and see what's inside. The address and the contents are two totally different things. So how does the computer actually get through that to-do list? It uses this super simple, elegant cycle, and it does it billions of times a second. First, the CPU, the brain of the computer, fetches the next instruction from a memory address. Next, it decodes it. It figures out what it's being asked to do. Add these two numbers or move this piece of data. And finally, it executes that command. Then, it just does it all over again, fetches the very next instruction. That's it. That simple loop is the heartbeat of your computer. Okay, so if that cycle is happening billions of times every second, the CPU needs incredibly fast access to its data. But here's the thing, not all memory is created equal. And that brings us to our second timeless concept, the memory hierarchy. It's a really clever solution to a fundamental problem of balancing speed, size, and cost. Let me ask you this, why doesn't your computer just have one giant, super fast chunk of storage for everything? Why do you have RAM and a hard drive and maybe a solid-state drive? Well, the answer is a classic engineering trade-off that's been around for decades. It looks kind of like this. At the very, very top, you have things called CPU registers. They are right inside the processor itself, and they are blazingly fast. But they're also incredibly expensive, so you can only have a tiny amount of them. A step down from that, you've got your RAM. It's a bit slower, but it's way cheaper, and you can have a lot more of it. And then way down at the bottom, you have your hard drive. Much, much slower, but super cheap for huge amounts of storage. You see the pattern, right? The faster it is, the more it costs, and the less of it you can have. So, the big takeaway here is you just can't have it all. You can't have storage that's super fast, super big, and super cheap. It doesn't exist. So computers use this tiered system. They keep the stuff they need right this second in the fastest, most expensive storage, and everything else gets pushed further away. It's this beautiful compromise that makes modern computers both fast and affordable. All right, let's move on to our third and final timeless idea, the universal language. This is all about how computers take our rich, complex world and translate it into the only thing they actually understand, numbers. Now this one might just bend your brain a little. To a computer, there is absolutely no difference between the letter A in an email, the color blue in a photo, or a single note in your favorite song. At their very core, they are all just numbers. Specifically, they're patterns of ones and zeros. That is the only language the hardware speaks.
And here's a perfect example of how that works with text. There's a standard code called ASCII, and it basically assigns a unique number to every character on your keyboard. So the letter A is just the number 65, which in binary looks like this, 0100001. When you type the word cab on your screen, your computer isn't seeing letters. It's just processing the numbers, 67, 65, and 66. It's all just math.
And it's exactly the same for images. A photograph isn't one thing to a computer. No, it's a giant grid of millions of tiny dots called pixels. And each one of those pixels is represented by a set of numbers that tells the screen exactly what color and brightness to be in that one spot. So that beautiful photo on your screen, to the machine, it's just a vast, intricate tapestry woven from numbers.
So there you have it. We've seen how these incredibly complex machines we use every day are built on a handful of simple, powerful, and decades-old ideas. So let's bring it all home and see why this really matters.
Let's just recap. We covered the stored program concept, the idea that makes computers flexible and programmable. We've seen the memory hierarchy, that clever trade-off that makes them both fast and affordable. And we've learned how everything, from a text message to a movie, is just represented by numbers. These three pillars, they haven't really changed.
And this brings us right back to Dr. Englander and his amazing idea of riding the wave. Look, the technology itself, the chips, the drives, the screens, that stuff is going to keep changing. It's going to get faster and smaller and cheaper. That's a given. But because you now understand the fundamental blueprint, you're equipped to understand those new developments as they happen. You're not just memorizing specs anymore. You're seeing the architecture.
So I'll leave you with this question. The next time you hear about some crazy new technology, whether it's artificial intelligence, quantum computing, or something we haven't even dreamed of yet, I want you to look closely. Because I bet if you look close enough, you'll find these same timeless principles from the dawn of the computer age still humming away right at the very core.